Today, the final video in the Trevor Tesla Coil series. Hello everyone, welcome to the Geek Group. I'm Paul Kidwell.
And I'm Trevor Kenyon.
We're here today to put the final touches on Trevor's Tesla Coil. We were working late last night, and as you can see, there's been some developments. We mounted the secondary, we redid the primary for like the third time, and we actually drew out and finalized the wiring that we're going to use for the coil. You're going to see some of that in a few seconds. After the break, we'll be back and show you how to put together an MMC capacitor. All right, so we're designing our Tesla coil here. I'm going to do the wiring on the whiteboard. We'll start at the right end here where we have our secondary coil going to our toroid at the top. Make it look a little more like a toroid. There we go. Okay, there's our secondary. That's this guy.
All right.
All right, now the next part is our primary, which we've got rewrapped again. This is like third time, right?
Yeah, it's been a pain.
We have the end of the tube now at the last support here. There's no notch in this one for it, so that's as far out as we can go. Spirals all the way into right here where we have our connection point coming out the bottom. So this is the primary, and this is normally wrapped around the base of this. I'm going to draw it out over here as an inductor.
Okay.
And it'll be some number of turns. We're actually going to have a tap point that we can move around. So you can go from winding to change your tuning point.
Okay. Well, what does that mean, though?
All right. This toroid forms a capacitor. The capacitor is two plates separated by a dielectric. The dielectric is the atmosphere. The one plate is the toroid, the other plate is the Earth. So there's a mathematical calculation to give you the capacitance of that toroid. It's affected by a lot of things like the room it's in and how close other things are. It can vary a lot, but we can get a close approximation. That capacitance with this inductance gives us a resonant frequency.
Okay.
What we want to do is we want to tune the rest of the circuit to match the resonant frequency of our secondary. Okay. And we have oscilloscopes and signal generators and all kinds of things to get that set in pretty close right from the outset.
So what happens if it's not tuned?
The better tuning you have, the better spark output you will get.
Okay, then we want it tuned.
Yes, we do. The one thing about tuning, though, is the sparks themselves affect the tuning. We can actually like take pieces, we took pieces of wire for Gemini and had a wire pulled off to simulate a streamer coming off, tied a string to the end and then got way back and then held the wire up coming off the toroid to simulate a streamer, and it had an effect on the resonant frequency.
So you can't win.
You can't, it's variable, it's going to change, it's dynamic. So you get it in a range or close to where you're expecting it to be while it's forming this length sparks you're going to have. Okay. So, but we can calculate that mathematically, and we can measure it with the signal generator and oscilloscope.
All right.
We'll be showing you that later.
Okay.
Anyway, this is the primary. It's another inductor. We are going to make the MMC with our caps. We have a nice supply of them with one out. Yes. We figured out we can use between 11. Let's see, 10 was 20,000. We can use between 11 and 24 caps. No, 11 and 15 caps to give us the right value.
And we chose 12.
And we're going to go with 12. That gives us a higher capacitance value, meeting the minimum voltage we need to keep the caps safe. Okay. All right, these are 2,000 apiece. 12 of them gives us 24,000 volts. And we're using a 15,000 volt transformer. That's RMS, so you multiply your 15,000 volts by 1.414, and it comes out with 21,000 and change, so we have a little bit of clearance. Hello, Moose.
That. Thank you, Moose.
Thank you, Moose. Moose has
now we have something to hold it on.
Moose has cut us a piece of plexi that we're going to use to build our MMC a little later. with holes nicely spaced to hold our
Yay.
caps. So
Now,
that will cover in a
one
bit.
question I did have
What's
with
that?
this. Are you soldering this end to the other end of?
Yes, you are.
Okay, we are doing that.
Yes, we are.
Okay.
And we have our
Resistors.
safety resistors, so we don't kill ourselves. Okay.
That's the risk is half the fun.
Okay. The rest of the circuit out here has two more components to it. The first is a spark gap, which you've built right here, which is actually a really neat.
Those were computer mounting brackets.
Yes, and I would maybe put a jam washer or jam nut on there so they don't move around while they're operating, but that should be fairly interesting to set. But that'll work wonders. You have a spark gap and you have your MMC cap. So I'm going to put, the position on these could change, but for the moment I'm going to draw them like this.
What is
And-
that? Is that the spark gap?
That's the spark gap, that's the cap.
Okay.
All right, now,
And then is this the NST?
no, the NST, we get to pick where we're going to put it. There's 3 connection points, there, there, and there.
And the difference between them is?
Now, you can hang your NST off here. So you'd have your 110 volts AC. Your spark gap is across your NST. The gap you set here will set the maximum voltage your NST will see. Are you doing any sort of Terry Fritz protection circuit? I think it's Terry Fritz, but are you putting a protection circuit in here at all, or is it just going
I've never
in?
heard of it, so I would say no.
Okay, something you might
maybe.
want to look into. There's something you can put in this space right here between the NST and the rest of the coil to keep any high voltages coming from the tank circuit here back into the NST and blowing your NST up.
You might want to do that.
You might want to do that. Anyhow, the benefit of this, people get religious about, does it go here, does it go here? That's going to be another ground here as well. Or is it? I'm going to leave that off for the moment. I think it's not, because our NST actually has a center tap ground on it to the case. Having the spark gap here means we're limiting the voltage that we're going to see on the secondary. We're not limiting the voltage you're going to see on the cap. There's one logic that says to put a safety gap over here to protect the capacitor. So if it sees any overvoltages, your arc jumps. That would make an awesome safety gap, as a matter of fact. You got enough parts to make another one of these?
I don't know.
All right. Might be something worthwhile to look at. It's something that we could actually rig up on the MMC plexi, really. Just a couple of bolts set at a distance far enough that it's not going to jump. You don't want your safety gap.
So 2 bolts here would work as a safety gap?
Yes, it's just you put them close enough together so that if your voltage shoots up way high, it'll arc at that point. Basically, you're picking the point where it's going to arc over.
Well, we should probably do that.
It's something worth considering.
And that's just a couple drill holes away.
Okay, so that's one way of doing it. The other way is to move this whole thing down over here.
Is there any difference in size of the bolts?
To my knowledge, no.
Okay.
It's more a question of how you want to protect your cap. I think across the spark gap would probably serve us better because we want to protect the NST. The MMC, if a cap dies, these are just a couple of bucks.
Okay.
And they're still being made. I mean, we can order them. I think we got them for $2.80 a piece.
Okay.
Something like that.
I thought they were going to be like $40 a piece or something.
No. These are not.
I'm
these
glad
are-
they weren't.
So these are replaceable. They're the more inexpensive part of what we're dealing with.
So
The
it's
NS
safer though to have the NST over the spark
In my
gap.
opinion, it's like we should have more protection between the NST and the tank circuit, but the spark gap will serve as a primary safety on keeping the NST from blowing
Well,
up.
then why don't we do that?
Okay.
That sounds better. Extend the life of my coil.
Now your NST has a case ground right there, so you can't really ground your primary. So if you run off of like microwave oven transformers, one end of the microwave oven transformer is grounded, and typically you would tie that to probably the inside of your primary circuit.
Okay.
Seeing your tap point is going to change where it is on the secondary out
Now,
here.
how do we change the tap point?
You're going to have a clip that'll clip on to the tube, and that'll be your connection point.
Oh, is that going to connect to the NST?
And,
Or where?
for what we got right here, your primary, this is the inside of the winding.
Okay.
So from this right here, we're going to go to one end of the MMC.
Okay.
MMC. Okay.
So this is the part under my...
Yes. And for seeing we have the tube coming out here, I'm going to say it would be more logical to have the transformer mounted side to side this way.
Okay.
Okay. So here's one connection point. We'll have that come to one side of your MMC. So this guy, let's, what?
I didn't catch it.
I hope that actually lived.
Push the button, Jabroni. Ah!
Like a Timex, takes a licking and keeps on ticking. Okay. Now, this is going to be our MMC. And we're going to mount this in this area. How we actually do the mounting, we'll figure that out later. But this tube will go to a connection point right here.
Okay.
All right, so we're going to have a bolt right there that'll connect to the tube.
Now, could a bolt actually screw into the tube?
Not really. It's copper, it's soft. What you're probably going to do is we're going to either solder or somehow fasten a ring terminal of some sort to this, or mash this out flat and make a ring terminal out of it to go to a bolt here.
Okay.
But that'll be one connection. You'll go through your caps all the way through to here. So this will be the other connection. This bolt hole here would be this point here. Okay. So from here, you're going to the spark gap and one end of the NST. So from right here, we could feed through to here and go to one end of the NST.
And then that
this guy
we'd
will
feed
mount
through both
here,
of these sides.
and you're going to go across the NST here. And then the other end of that here will be your tap point, which you'll run up to one of these windings up here.
Okay, so we have 4 options then.
You have 4 options. Actually, you have more than that, because you can go like, you run your wire up, under, and connect over here.
So every single one will give a different...
You can fine tune that closely.
Okay.
All right. So there's our layout for how this is all going to be together. We need to get working on our secondary mount.
Which means we need to figure out how long we need to cut these.
We need to cut those. We need to drill some holes to mount this. This is actually going to be underneath.
So we need a
So we
3/8
can
bit also.
We need a 3/8 bit to clear those. And this is going to be adjustable to raise and lower. You can also bolt it directly to the top. But I think we're going to start out with it having it as tight up here as
So
we
worst
can.
case scenario, we bolt it to the top.
Yes.
Okay.
All right. And we're back. We're here today. We're going to put together an MMC capacitor. Now, we had Moose cut this beautiful piece of plexiglass for us. We are going to make an MMC that uses a single string of 12 capacitors.
Okay.
Now, we're using the Cornell Dublier. These are 942C20P15K-F. They're 2,000 volt capacitors, 1.5 microfarads. We're going to have 12 of them in series, so it would be 0.15 divided by 12 for the actual capacitance. As I recall, it's somewhere around 12 nanofarads or so. Having 12 of them in series, they're 2,000 volts apiece, so we got 24,000 volts for the maximum voltage on these, okay. Which is well above our margin for the NST we're using. The NST is a 15,000 volt transformer. That's RMS voltage, so you multiply by the square root of 2, 1.414, to get your peak voltage, which is somewhere over 21,000 or so. So we have like 22,000 volts with 11 caps would work. We put one more in just to give us a little bit margin of error. The resonant frequency we calculated before would be like 10.6 nanofarads, and that worked out to be, I think, 14 caps. Okay. And you want something a little bit higher than your resonant capacitance. So we're going to go with 12 to give us whatever that works out to mathematically. I don't remember off the top of my head. Okay. But we have the leads bent on our capacitors, and these will go through holes that we had Moose drill in this sheet of plexi. She used the sheet router to do this over in the MDH, and our holes are nice and neatly positioned to take the capacitors. We've included mounting holes and a place to have a couple of, I don't think it'll show up on the screen, but there's 2 holes for connection points to electrically hook up to this. Okay. Now, we have our 0.15 microfarad capacitors, 2,000 volts apiece. We also have some 10 mega ohm half-watt resistors. These are for safety. When you shut your coil off, there'll be voltages on these capacitors. They'll hold the voltage for quite a while. So we have the resistors, 1 resistor on each capacitor to bleed the charge off when you shut things down. We can mathematically calculate later how long it'll take for one of these to discharge one of these. But you put a resistor on every capacitor. There's some people that used to think you could put one big resistor across the whole thing and it would bleed it down. But what we're doing here is we're putting a bunch of capacitors in series. And when you do that, you could have like positive 2,000 volts on this one and negative 2,000 volts on that one. Right. And end to end, it would be 0. But you get between an end and a midpoint, and you're still getting 2,000 volts. So we put a resistor on each one. Now, we've pre-bent the leads. It's a 90-degree angle. We put a little spacer in there so we get a little bit of a radius on the end. And we lined them up so all the text would be on top when we stuck them in the plate, because we're trying to do art here. So... and we'll arrange them the same way. Before you go too far, we're going to have them on the bottom here. And once we get them on, we're going to wrap the resistor around the legs, literally going right around.
Okay. Are we going to need pliers for that?
I have my Gerber tool that'll do just fine. Okay. But it's just wrap it, just one turn around so that it's mechanically connected. We will be soldering it as well, but your solder can get hot, it can run off. I mean, things can happen, and we want, this is a safety feature, so we want the connection to be mechanical as well as just solder. Okay. But we're going to get all those on, and we're going to bend the leads to connect these together, which you'll see the pattern once we get them all on. And once that's done, we're going to add, slide some of those over. We have 1/4-20 bolts, and ring terminals, and washers, and nuts. So we're going to make some nice solid connection points on this so you're not trying to clip on to just the leads coming off the capacitors. Okay. So let's get started. All right, so we got our first two capacitors here, and I'm going to wrap the leads of the resistor around, and
There you go.
I'll
You like, yeah, you got your fancy
Gerber
one.
Ninja.
Your fancy one.
Yes. So you just bend it, or you hold it in place and bend it around.
Want me to hold it?
Now I got it with my fingers here. So there's one end.
So now if the solder melts, that'll still be on it and can still
Correct.
bleed the
And when we bend the leads on this, the long lead from the cap will actually be laid along the plexi, so it'll hold that down.
Right.
All right. So I got that end. Now I'm going to do this end. Okay. So there's my leads are bent around both ends. This one, we already know our pattern. This one is going to go to the next row up there. This end is going to go over here to the cap next to it.
Okay.
All right, and when you bend things, you kind of unwrap a little, so you need to repinch from time to time. It's actually going down into the hole, which may give us a little trouble when we go to start soldering.
Oh.
And I'm going to try and keep all the color bands going the same end. It's not vital, but it's more artsy. I mean, we want this to look good.
Yeah.
So here I'm bending the lead around this end.
Do you want me to start putting ones in on this side?
As soon as I get this done,
Okay.
we're going to put all the caps in and then start bending our resistor leads.
Oh, okay.
See, when I'm wrapping one, it's pulling from the other end, and it'll start unwrapping the other end.
Oh, I see.
So I mean, it's kind of like you do one, and you got to keep the other end okay. There. So then this lead goes that away, and there'll be, and that lead goes that away. So there's going to be a solder joint there, 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 there. So each cap is going to have two solder joints under it, plus one going to the next cap.
Okay.
All right? So let's load up our caps. Okay, well,
Caps.
there we have our MMC capacitor.
That one.
We can take a meter on this and we'll get a measurement to see exactly what our capacitance is. But we have a couple of nice connection points that we can use ring terminals to do our wiring to. And we'll be mounting this around the front of our little base here. So there you go.
All right. Sweet.
And we're back again. We've moved out to the MDH. We're about to have first light on your coil here. We're all wired up and ready to go. Once we get this and get some sort of output, we'll start tuning after that.
All right.
So I'm going to go set the gap on the spark gap and then check the wiring to make sure we're all set. Then we'll be good to go.
Okay.
No, it is not. That 15,000, it's not off of that bolt at all. You got it off with any bolt out. Shut it off? Yeah, bring it down. Okay, give me the alligator clips. Ready? Bring it up.
Not in tune. Oh, for those of you watching, don't look at the line. It's the same as a welding flash.
Go.
All right, guys, so that's the close of the final video on the official main construction of how to build a Tesla coil, Geek Group style. Okay, Thank you, both of you gentlemen, for getting in on this. It's cool, it's good, but it's going to get a lot better. So we're going to do some follow-up with this, because we've got it making sparks, but it's like just barely there, like just it's functional. Now's the real work of we've built it, now it's getting everything to play right, and that takes a lot of time and a lot of work. Okay. So, but you have to leave because you have to go to prom.
Yes.
So we're going to stop for tonight. We'll be back. There'll be more videos in this series, but that closes the official, we built a Tesla coil, it works. Now it's all the fun of getting it tuned. So you guys have fun. I'm Chris Bowden.
And I'm Paul Kidwell.
And I'm Trevor Kenyon.
And of course, we will see you next time.
This video was made possible by a grant from the Future Girl Foundation.
This video was made possible by thousands of private donations from members and viewers like you. Please visit thegeekgroup.org for more information on how you can donate and become a part of our dreams of Avalon.